IC roadmap, and we discussed some of the short channel effect of FET MOSFET. We have discussed high K dielectric. We have discussed strained silicon. We have also discussed metal gate versus poly gate, which gate we should use, or which gate has been using by industry nowadays in this short channel MOSFET. We have briefly mentioned about SOI. SOI is, as I told you before, SOI is silicon on insulator, where there is an insulating layer between handle silicon and the active silicon, or in other words, the active silicon is on top of buried oxide. That is why it is called silicon on insulator. So active silicon layer on top of one insulating layer, that is buried oxide, made of SiO2, and all the devices we fabricate in this tiny thin active layer, and that has, I mentioned, that has several advantages. One of the advantages is the capacitance associated with source and substrate, and drain and substrate can be reduced drastically, because now there is additional buried oxide, and the capacitance is between source and through buried oxide to this handle silicon wafer. Okay, and this buried oxide is maybe a few micrometer thick, right? So that is how the capacitance associated with source and drain with the substrate reduced. That improves the performance, and also the active silicon layer can be aged or removed in different places where it do not need. So that is how you can remove the crosstalk or leakage current between one device to another. Okay, because in conventional CMOS wafer there is a continuous silicon substrate. Okay, and you need to isolate devices for adjacent devices through various means. But here you can basically etch the active silicon layer where there are no devices, right? And so on and so forth. So these many advantages gives rise to a lot of improvement, and you can reduce the device dimension even further. And as I said, like this is an example where industry reported 250 nanometer gate length node can perform as good as 180 nanometer gate length node of SOI can perform as good as 180 nanometer gate length of CMOS wafer, right? And then we also mentioned in the last class more mood and more than mood. As we told that more mood is basically every 24 months we are reducing the dimension of the MOSFET, so that's more mood, and we have been doing that for last 50 years or so. But here we are in a position now where it is very difficult to sustain that continuous progress, simply because it requires lot of money and a lot of new innovations, and that is not giving us value for money, in a sense. That is not giving us enough advantage, right? And we are in now in the atomic scale. It is very difficult to reduce the dimension even further. Now probably we are in the 7 nanometer gate length, 7 or in fact 3 nanometer gate length we are at the moment. So it's very difficult to reduce the dimension even further. Okay, and as I said, no real performance increase with the scaling we are achieving at the moment, and expensive or R&D manufacturing cost is huge, right? So people are looking for more than more, where you not only have like advantage of reduction of transistor sizes, you also incorporate other functionalities. For example, you can use sensors, different kinds of sensors. Nowadays, the electronic gadgets has many different kinds of sensors, right? You can use the optical devices. You can accommodate the power devices, RF, MEMS, and NAMES, okay, and so on and so forth. The only issue is then like these like sensors, MEMS, names, they are in the not CMOS process line. They can't be fabricated in the CMOS foundry, right? So you have to fabricate in the from a different foundry and need to integrate them. Or if you want to foundry from, say, if you want to fabricate from the CMOS foundry, you have to change the fabrication process of conventional sensors and MEMS and names and so on and so forth. So it is not easy to accommodate them in the conventional CMOS process line, but if you can do that will be excellent, right? So as I mentioned here, that incompatible with CMOS, that is one of the challenge. Okay, they are bulky like sensors and MEMS based devices. They are not as tiny as your FET, right? They are bulky compared to your conventional CMOS process or CMOS devices. Okay, in one hand they are bulky, they are incompatible with CMOS and often unsuitable for mobile platform, right? So all these you have to take into account if you want to integrate different functionalities with the conventional CMOS process. But that is as we have been seeing last 10 years or so, that is the way forward, and that is we are saying more than more. So we definitely need more than more to go forward, because only reduction of device size is has not giving us enough advantage. Okay, now this is the probably the last slide we have discussed in the in Tuesday's class, and this is where we are showing that you see in the y-axis you see we have written process nodes like 130 nanometer process, 90 nanometer process. So by 90 nanometer process I mean like the minimum gate length possible in that node is 90 nanometer, right? If I talk about 65 nanometer process, that means minimum gate length possible is 65 nanometer, and so on. So so every 2 years down the line we are reducing the gate length. So that is following the Moore's law. Okay, Moore's law of miniaturization. But as I said, like we also we have been integrating analog, RF, passive devices, different kinds of active devices, sensors, bio chips, and so on and so forth with our electronic gadgets. So instead of going in this y direction, we are also incorporating other functionalities. So that way we are moving in this direction. In this direction, you see here combining SoC and SiP. Okay, on the same system, or making a same system. Okay, SiP is system in package. So in a package you can integrate different systems, maybe sensors, maybe power devices, maybe your CMOS, and so on and so forth. So that's basically system in package, and SoC is system on chip. Okay, on a single chip you can make several systems like a processor and so on and so forth, or maybe very application specific specific integrated circuits like your ASIC chip, right? So that is same system on chip, and here we are talking about system in package. There are different kinds of system, and you can put them, so those are different ICs, and you can put them in a single package and to make it system or in package, right? So you want to integrate these two, you want to accommodate these two, so that you can have like we can move on, right? So now no, so this is one direction, as I told you probably before. So the nanoelectronics research are moving into parallel, have been moving into parallel direction. In one direction, we have been reducing the dimension of the devices, and in another direction we will look, and those devices are based of silicon or gallium arsenide. But in another direction we are trying to, or we have been trying to develop other materials, to realize our nano electronic devices, okay, or nanostructures. So these materials are different. They are not silicon based, or they are not gallium arsenide based. Okay, these materials are usually made of, say for example, carbon nanotube. They are made of graphene. So these materials we will discuss later on, but let me just point out about those. These materials may be metal oxides. Of course, their silicon has always been there. Okay, and so on. So metal oxide, for example, zinc oxide, tin oxide, the tungsten oxide, and so on and so forth. So these are other materials compared to silicon, conventional silicon or conventional gallium arsenide. So these materials can't be developed in the CMOS foundry, because CMOS foundry usually doesn't allow these materials to make in their foundry. Okay, it is mostly silicon or gallium arsenide 3,5 semiconductors. So these are different materials. Why people have been doing research in that direction? Because there were times when the silicon based MOSFET, we thought that we will not be able to progress anymore, okay, progress further. So there were the barriers, and people then came up with a lot of different innovative solutions to nullify those barriers. For example, we talk about strained silicon, because there were degradation in mobility. We talked about high K dielectric, because there were leakage current and reliability issue of gate oxide, and so on and so forth. So there have been different short channel effects, and the performance of the device, the silicon based MOSFET degrades, and then people thought that we will not be able to move with silicon, and they started doing research for using different materials, because these materials have some way or other maybe advantages compared to silicon, right? So so these materials people have been venturing in their lab, rather than these are developed in industries. So industry will pitch in, as I said before, if they showed sustained development, or they showed real advantage compared to that of silicon. But as of now, industry is very happy with silicon and gallium arsenide and all that. Now these nanomaterials, they can be used to develop various structures. For example, nanotubes, nanorods, nanopillars, nanoparticles. What are those? I will show you some pictures in a minute. But what is nano? Nano is basically, the nano is 10 to the power minus 9 meter. So roughly less than 100 nanometer, we can call it a nanostructure. Okay, although there is no hard and fast definition, but roughly we consider less than 100 nanometer is a nanostructure. And nanotechnology is basically the technology which fabricates or deals with such structures, or develops such structure or devices of this order of a scale. Okay, less than 100 nanometer or so. Now so this for example, this is you see hexagonal honeycomb structure. Okay, this is a structure of graphene, right? Again, I will discuss all these things in more detail later on. This is just a bird's eye view I am showing. So this is like graphite. Graphite is a stacks of this honeycomb kind of structure, and if you can remove one of these layer, and then you will get graphene. So graphene is basically single layer or mono layer of graphite, right? So this graphene layer, if you manage to roll and make a tube like structure, that is basically nanotubes. Okay, so this nanotube may be a single layer, this nanotube may be multi-layer. Okay, if this graphene like structure you can make a ball kind of a shape, then it is called buckyball. Okay, usually made of fluorine, and so on. So so as I said, like these carbon nanotubes can be multi-wall or single wall. If this is a single layer, then we call it single wall carbon nanotube, and if this tube is multi-layer, then we call it multi wall carbon nanotube. Okay. And there are different ways to grow them. Again, I'm saying I will discuss this in more detail. So just skip all these slides. This is how you grow carbon nanotube, and this is how the carbon nanotube looks like. Anyway, I will come back to these later on. So for example, this is an old slide where a professor is showing a wafer, the silicon wafer. On top of that, he managed to grow 4-inch silicon wafer all over the wafer carbon nanotube, and so forth. So for example, this is graphene. Nowadays, not only this nanomaterial based structure people have been developing, there have been a lot of applications. So people are trying to get or develop applications so that these material can be used. Okay. And I mean, they are not in fight to replace silicon, to be honest. Now they are more to take the advantage of both. They want to take the advantage of silicon, they want to take the advantage of non-silicon based materials. So there have been a lot of applications of this nanomaterials which are not silicon. Okay. And nanostructures. So one of the application is you see flexible electronics. So you can by flexible I mean you can develop your system on a piece of paper. You can develop your system on clothes, on plastic. Maybe you can have your TV on a piece of plastic paper. You can roll that and take it in your bag, and maybe you went somewhere, and you've gone somewhere, and open your foldable TV, and switch on, and everything will run. So there are flexible mobile phones are coming up. A lot of companies are venturing into it. For example, Samsung is one, and so on and so forth. So flexible electronics is one of the very important applications of nano electronic based devices. Okay. Now this graphene based material first developed experimentally by Andre Guillaume and Novoselov, okay, from University of Manchester, England, and UK, and they were awarded Nobel Prize around 2010 for their development of graphene, experimental development of graphene. Graphene have been around much before 2000 or 2005, at least theoretically. Okay. But they have developed it experimentally for the first time. Now these are some of the images I would like to show you, to tell like how the nanomaterials looks like. So these images were taken using a microscope known as a scanning electron microscope, or SEM. Okay. SEM, scanning electron microscope. So these scanning electron microscope are different kinds of microscope. Again, that we will discuss. So these are SEM images. Sorry, let me write it once more. Why it is happening? SEM images. Okay, scanning electron microscope images. So you probably know about optical microscope. Through optical microscope, you can see small things. Okay. But the thing is, in optical microscope we use light, visible light. Okay. And the wavelength of visible light, say around 400 to 700 nanometer, because that's the visible range. But here the nanostructure is much more tinier than that. So you can't use optical microscope to see nanostructures. So you need so you need electron microscope. Okay, one of the electron microscope is scanning electron microscope. As the name suggests, here you need to you use electron to scan the surface of your nanostructure. Okay, and then you can get image. So we will talk about scanning electron microscope later on, just to show that how these different nanostructures looks like. For example, this is a nanoforest of multi-wall carbon nanotube. Okay, this is single aligned single wall carbon nanotube. This is, for example, zinc oxide nanowire. Okay, these are the images of silicon nanopillar. Okay, silicon nanopillar. These are different nanoparticles, and in between nanoparticles there are nanowires, right? So this is a W03 nanoparticles. So these, when you see when you take a scanning electron microscope image, you see there is a scale bar here. Okay, from there you can say that how much is the dimension of individual nanowires. Right, through that microscope you can measure the dimension, you can measure the surface, you can check the surface morphology of your nanostructures. So very handy tool, and this kind of tool which is different from the different in a sense ki you need such tools to see your nanostructure, because they are beyond the visible range, right? And this is how the nanostructure looks like. Now, one point I would like to mention here, as you see, like it is not easy to develop nanostructure at a very specific place, particularly for non-silicon based devices. When we talk about non-silicon based devices, for example, multi-wall carbon nanotube or single wall carbon nanotube or nanowires and so on and so forth, these are not easy to develop in a very specific place over and make like several million of them. Okay, it is not easy. Still we have been trying that, right? Whereas in case of the conventional silicon based MOSFET, you can very accurately fabricate those sub 100 nanometer, in fact 22 nanometer, 15, 14 nanometer, 7 nanometer, these gate lengths based MOSFET is a more mature technology. We have to fabricate those. Okay, so we can have like billions of devices on a single wafer with very accurate device size compared to all this nanostructure which I am showing now on the slide, right? So, so although we managed to develop such nanostructures using different materials, but the technology is not that mature to challenge the conventional silicon, right? So, so that is why what I am saying, that the initial perception was we will develop FET based devices out of these nanostructures because they have some advantages compared to that of silicon, right? But later we managed to move with silicon and managed to reduce the device dimension. And so these nanostructures are still in the research domain, and we are trying to develop different applications rather than fight with silicon that we have to make a FET out of these different kinds of nanomaterials, right? So let's now move to a little bit different aspect. Okay, this different aspect, I would encourage you to go to this website. Okay, I would encourage you to go to this website and see stuffs there. Okay, so this is so there was an organization, I'm saying was because this is no longer there. This organization is known as ITRS, or International Technology Roadmap for Semiconductors. So International Technology Roadmap for Semiconductors, so this was an organization which if you go to their site, you will see that this organization was this is an organization which basically predict 15-year assessment of the semiconductor industry. 15 years. So if you predict today, I mean, if they predict today, they will predict for 15 years how the semiconductor industry will progress in next 15 years. Although this organization no longer exists, but when it was functional, it was basically predicting what will happen 15 years down the line as far as the semiconductor industry is concerned. So it talks about the future technology. It talks about present status of technologies, what are the future technologies, how to move and achieve there, go there, and so on and so forth. So these future needs drive present day strategies of the worldwide research and development. Okay, so their forecast basically talked about what is the present status, what will happen in 15 years down the line, how to how to go about it. Okay, what are the strategies should the worldwide research and development development in industries and also in academia, people should follow, and so on and so forth. Okay, universities and national and international labs and so on. So this is a very important organization which drove this nano research over the years. Okay, as I said, like, you should visit this lab, this website, and you found more information. I'm just giving you I'm telling you very little about their functions. Now these ITRS started around 1998 because people thought about, like, we should have an organization which will forecast and drive Moore's law. Let's put it this way. Okay, although it's not only about Moore's law, but as the industry has been following Moore's law from 1965, 1970s, they thought that we should have an organization which will basically tell us the status, present status, as I said, and also the future requirement, the future direction of semiconductor industry or nano electronics progress. Okay, at the initial stage it was not nano, but of course over the years it became the gate length became so tiny that it becomes nano, right? So this organization was there for started around 1998, and it was there till 2015. Okay, and the semiconductor industry experts and the people from academia, experts also from all over the world, Europe, Japan, Korea, Taiwan, US, they were there in the committees, different committees, to forecast this. Okay, as I said, its primary purpose was to serve as main reference into the future for university, consortia, and industry researchers to stimulate the innovation in various areas of technology, nanotechnology. Right now, so these are different handful areas where they predict things, they assess the present status, and they predict things. Okay, for example, IC interconnects. So interconnects is vias and the metal tracks, different research materials. Okay, emerging research devices. It not only conventional field, there have been many different research, different innovative devices over the year. Over the year, people managed to develop. Okay, and so on and so forth. So these are different areas where they thoroughly forecasted things. Okay, now so this is a very old slide, old in a sense ki it was if you go their site, there are slides which is newer than this one. This is, I think, the prediction around 2008 in their roadmap. They predicted that in 2008 about all these fields. Okay, and they predicted, like, so you see these hashed lines are showing continuous improvement. Okay, if you look at bold black lines, so this is research required. Okay, and you see, just want to point out here. Okay, say carbon nanotube, nanowire, graphene. In 2008 they predicted, like, we need research, we need research till 2020 2021. Okay, in these new materials and new nanostructures. Okay, so that the industry can take these kind of nanostructures and nanomaterial later on in their process line, right? So beyond 2020 2021, it will be development underway, right? So before that, it's like extensive research is required. So what I'm saying, what I try to point out, that so these are different, as you see, these are different years. So at 2008, they have predicted till 2024. Okay, as I said, it is like 15 years prediction. So these are very important information, and what I want to point out is, like as I said before, although people managed to develop and have been developing different nanostructures and nanomaterial, initial focus was to compete with silicon or to replace silicon, but over the time silicon we managed to develop again, removing all the barriers and all the short channel effects. Okay, most of the short channel effects. So, and the progress with these nanowires or with these nanomaterials is not at par with silicon. Okay, so what we have been trying, we are trying to develop different applications to which can go hand in hand with silicon based MOSFET. We are no longer, I mean, I will not say we are no longer interested. We are interested to develop FET based devices with these materials, but we are more interested to develop other applications, and so that we can take advantage of conventional silicon in one hand, and these non-conventional non-silicon materials in another hand. Okay, so this ITRS is no longer there after 2015. So after 2015, they have developed a new organization that I will come in a minute. But let me tell you one more thing. You see, like these are different process nodes. Okay, these are different process node. As I said, by process node I mean the minimum gate length possible in that particular node. So when I mentioned like the 90 nanometer process, that means the 90 is the minimum gate length. If I say 130 nanometer process, that is 130 nanometer gate length. Can anyone tell me like how I am coming to these numbers? Why the 180, then 130, then 90? How these numbers are coming? Do you know? Do you know how these gate length numbers are coming? Why it is 45, then 45, then 32? Why it is not something in between, or why it is not after 45? Why it is not 25? How these numbers are coming? Do you know? Any answer? Yeah, go ahead.
Like we are decreasing the area by 0.5, so the length is decreasing by 0.7. So 130 into 0.7, approximately 90.
Right. So you see, yes. Yeah. So you see, we are reducing the area, making it half, right? Every 2 years, every 18 to 24 months, so that we can have the density, we can to make double, right? So if you see like here, so 45 into 45 into like 45 nanometer process. Okay, so that's basically area is of this order. So the next node, they are made like 32 by 32. Okay, so that they can make the area half, roughly half. Okay, and so on. So these are different process node. Okay, um, and as I said, so this node is minimum gate length possible. Okay, minimum MOSFET gate length possible. But a very important point I would like to mention, that although we have been following Moore's law over the years, but what happened is in 1997 Intel started introducing more aggressive gate length, right? So they thought that they can reduce the gate length even further. Why should we follow Moore's law? We can go beyond that. So they started, Intel started introducing more aggressive gate length, okay, scaling, gate length scaling. For example, their 0.25 micrometer process had gate length of 0.2 micrometer, and 0.18, that is 180 nanometer process had gate length of 130 nanometer. Okay, although the numbers they maintained, okay, these numbers they maintained, they said like this is the process node, but their actual gate length was lower than whatever quoted in this process node. Okay, so process node was effectively larger than actual gate length what Intel came up with. Okay, the process node, but in usual sense, so when we talk about say 45 nanometer process, that we usually mean 45 nanometer gate length. But what I'm saying that what Intel did it for their design and their fabrication, they have their own fabrication lab. What they did, like they started scaling down more aggressively than Moore, and they although they said like they will follow these 250 nanometer, 180 nanometer, 130 nanometer process node to have parity with other industries. Okay, or not to confuse others. But the thing is, they actually reduce the gate length even further in all those process nodes. So the process node was effectively larger than that of their actual gate length. Okay, now actually what happened what happened actually is there became two groups. Okay, one group was which were developing microprocessors. Okay, and they were basically pushing faster clock to get more performance, right? In microprocessors, when you buy any electronic gadgets, you always look for how fast it is, right? So that's basically the clock speed. Okay, so there are basically two groups. One was like microprocessor developing groups, okay, which were pushing for faster clocks to get more performance, and so they were trying aggressively shrinking the gate length. So you have to reduce the gate length to improve to make the device faster, right? So they were pushing the reduction of the gate length. While there were another group which is basically memory based group. Memory is huge industry. Okay, has been huge industry because we need memory in all our devices. Okay, so memory memory developers, they want different things. They want like they want what to say, they want the metal lines should be as narrow, and also their separation should be as narrow as possible. Okay, why? Because in memory you need so many right read lines, write lines. Those are metal tracks or metal lines, right? So they want metal lines as close as possible. Okay, so that you can lay out or you can fabricate as many metal lines as possible. Okay, so the memory people want they were pushing or they were trying to reduce the half pitch, that is the separation, say roughly the separation, in order to cramp more bits into the chip. Okay, in order to cramp more bit into the chip. So this in part led to a divergence. So one group wants to reduce the device size, and another group wants uh, to reduce the distance between two metal lines, right? Two adjacent lines. So these create a divergence. So Intel in 65 nanometer process in 2005, the gate length was 32 nanometer, and the half pitch of the metal one line was 105 nanometer. Clearly the original node definition had been tossed to this side, right? Because 65 nanometer by 65 nanometer, we mean like 65 nanometer gate length. but the 65 nanometer Intel process in 2005 they were in fact using 32 nanometer, and the metal half pitch of the metal one line was 105 nanometer. But as I said, like historically there has been debate whether to reduce the whether to reduce the gate length or to reduce the pitch, that is the distance between the metal lines. Okay, I'm not talking about the distance between metal 1, metal 2, metal 3. I'm talking about distance between the same I mean in the same layer, the distance between different metal lines, adjacent metal lines. So for memory people, adjacent metal lines distance is very important. For the processor people, the device dimension is very important, and so on. So these are some, so this is some histories. Now the thing is, as I probably told you before, but let me reiterate once more, the final international roadmap, the roadmap, international technology of roadmap, that is ITRS, semiconductor ITRS, that is international technology roadmap for semiconductor, is now out. Out means it is probably published in 2015 or 2016, because until that it was functional. Okay, and in the past, let me say it once more what I have said already. Moore's law continued past 50 years by morphing from one scaling method to another, because we have come across several scaling methods and several difficulties that they try to manage. The people try to manage or sort out all those difficulties through different technological innovation. Okay, and we have situations like we started with bipolar transistors, although but because MOSFET, initial days MOSFET development was very difficult. Fabrication of MOSFET was very difficult. Okay, so people managed to fabricate bipolar transistor in initial days, but then they realized it is not easy to scale down bipolar transistor. Okay, so bipolar transistors were replaced by PMOS, because initially NMOS we couldn't fabricate NMOS for various reasons. Okay, because we couldn't get positive threshold voltage, right? Then for NMOS, basically we need to dope boron in the channel to achieve NMOS, okay, performance. And before ion implantation it was difficult to do, and so on. So let's not go in that direction. What I'm saying, that initial days it was bipolar transistor, it was replaced by PMOS, and then it was replaced by NMOS, and later on we have it like CMOS, both PMOS and NMOS together, and so on and so forth. So now the thing is, we even now are looking for things to make in things in vertical dimension. If we get time, we will talk about TSV, okay, through silicon via what is that technology and all that, if we get time. So we are instead not only reducing the dimension in the X and Y direction, we are also trying to integrate things in the Z direction also. Okay, to reduce the footprint and so on. So so what people thought, that ITRS is not the platform to way forward. So people develop a new platform to assess things, which is known as IRDS. Again, you should go to IRDS website and learn more about their functionality. Okay, I think it started around 2015 2016, and it is done by IEEE. Okay, IEEE just started a general road mapping project, because you see, ITRS main focus was semiconductor. Okay, main focus was semiconductor, how to reduce fed devices and so on, how to accommodate more and more fed devices and so on. But this IRDS, that is international roadmap for devices and systems here, because as I said, like now we have not only semiconductor devices, we have sensors, we have biomedical devices on the same electronic gadgets, right? So that requires different expertise. So that is how the ITRS is no longer there. Rather than ITRS, we now have IRDS. IRDS is basically looks after different kinds of systems, not only semiconductor technology, but other technologies also which can pitch in and evolve and give value for money of your electronic gadgets. Okay, so that is how this, instead of ITRS, a new platform or new organization was developed, that is International Roadmap for Devices and Systems, or IRDS, and this is under IEEE. Okay, now this let me just mention briefly, as I said to you before, this organization, again, please go to this site and look more about more info about this present trends or present roadmap of semiconductors and beyond semiconductors. Okay, so you see the focus is spreading well beyond the limits of CMOS devices and related technologies. This is the focus. Okay, so that is how this IRDS was developed, because it's no longer only the expertise from semiconductor industry. We need expertise from other industries and other academia platform also. Okay, and so in May 2016 it was established. Okay, again it also, I think, it also gives 15-year horizon. Okay, so 15-year focus or 15 years prediction of in which direction it is we are moving, challenges, potential solutions, opportunities for innovation, and so on and so forth. Okay, and it encourages collaborative research worldwide, research between industry and academia, and so on and so forth, so that we can move to a better world. And so this the focus is now in a little bit different direction. As I said, beyond CMOS, there are a number of critical domains and technologies of IRDS includes in greater detail. For example, probably you have heard all these cloud computing, cyber physical systems, which basically looks after safety and security of your system, mobile technologies, Internet of Things, that is IoT, and so on and so forth. So beyond CMOS is just one aspect in the evolution of computing, right? So computing is coming in a very big way, or electronic gadgets coming in a very big way. So in the we not only look for device, circuit, logic gates, and functional block systems anymore. We look for things beyond that. So in this new organization, they not only look for silicon-based system, silicon-based material. They look for other materials, for example, tin oxide, okay, gallium nitride, and so on and so forth. Graphene, all these materials they are looking for. They are assessing their prospects and how to bring them in the industrial process line, and so on and so forth. Okay, so I'm leaving it here just to give you some insight about ITRS and IRDS, and if you get time, please see their sites. You will get a lot of information about the present status and present scenario, and what is the way forward, how the industry and academia will progress in nano electronics, right? Now, what else? So let me just briefly mention as I said, the fight. I mean, there have been development towards making making this non-silicon based FET. Okay, but as I said, people also have been trying to take the advantage of both. Maybe some materials like graphene, tin oxide, and all that, they have advantages to develop some different applications. So the people, what they have been trying to push those applications, and if we can integrate those applications with conventional IC. Okay, so as that is why I'm saying that nano integration with CMOS. Okay, so we have mature CMOS technology. We can have very we can have reasonable accuracy and expertise in developing the FET based devices and integrated circuit, application specific integrated circuit. So we should take that advantage from the CMOS side, and we develop other devices using other nanomaterials, which is not possible using silicon, maybe possible with graphene or maybe possible with tin oxide, zinc oxide, etc. And how we can integrate those two in the with CMOS, how integrate those devices like sensor devices and so on with conventional CMOS. Okay, so this is nano integration with CMOS. So what is the advantage? Advantage is so if we can manage to integrate them, then device and circuit will be on the same silicon die. Okay, device, and so if we can integrate that in the CMOS platform, then device and circuit will be on the same silicon die. So those sensor device and the circuit will be on the same silicon die. But what is the constraint? The constraint is a lot of constraints are there. So for example, if you want to make your own material which is like different, maybe graphene or carbon nanotube, and want to make a sensor, okay, then you have to either come up with a synthesis process or a fabrication process of those material where you don't use no longer use harsh chemicals, no plasma, etc. You can't use. Okay, you can't use high temperature. If you use high temperature to make your material, your metal might melt. Okay, metal tracks might melt. So you require novel methods. So that's very challenging to develop your sensors and other devices, right? Non-silicon devices. So what you can do, you can come up with some post CMOS technique. So your CMOS foundry will not allow you to make things in their own foundry. They will make the circuit for you. They will give you the circuit, and you can then develop or make your sensors. Okay, so you can have like your materials different from silicon material, and you can deposit those material on area where you will make the sensor on the same silicon die. Okay, now so this is one of the example where I'm showing like we made carbon nanotube here. These are carbon nanotubes. Okay, this is an optical image, so you can't see the nanotube. Okay, you see these black spots, but you have to believe me, these are CNTs, carbon nanotube. And you see this is a CMOS chip. These are CMOS chips. So in a CMOS wafer, we make carbon nanotube, okay, on the silicon wafer. Okay, then you can dice or cut the wafer to separate chips. These are bond pads. So these are pads where you can bond the wires to the package and access from outside. Okay, so these carbon nanotube, with the way we made, I mean, it's not important for right now, but just let me tell you that in case of carbon nanotube, let me go back. Although I said that I will not I will discuss that later on, but let me just go back to this slide. So this is how we make carbon nanotube. So we have a substrate. On top of substrate, we deposit catalyst. Okay, and this catalyst basically we heat it up. So this catalyst forms small island. So this heating is important, maybe, and then we use 600 to 800 degrees centigrade and put it in a PCVD, plasma enhanced CVD chamber, chemical vapor deposition chamber. So what are these? We will come later on when we will talk about carbon nanotube fabrication in more detail, but just let me lay out what are the process steps. And you see you need 600 to 800 degrees centigrade, and in the plasma enhanced chemical vapor deposition chamber there are gases. Okay, so those gases basically carbon containing gases, which will basically dissociate and push those catalysts. You see, push those catalysts to make carbon nanotube. Okay, so this is the scanning electron microscope image of a small tiny catalyst island. And when you pass, so these are small tiny catalyst island because of heat treatment. And when you put it in the PECVD chamber 600 to 800 degrees centigrade, you manage to have like the carbon nanotube with this shiny top, which is basically those metal catalysts. So these catalysts are maybe iron, nickel, cobalt, and so on and so forth. These can be used as catalyst. And here you see they have used C2H2 gas, that is the carbon containing gas, which will basically dissociate within plasma enhanced chemical vapor deposition chamber, and that is a source of carbon which will push this catalyst to form carbon nanotube. Let's move on, and this process, if we apply your metal tracks will melt at 800 degrees centigrade, because you need 600 to 800 degrees centigrade. Carbon nanotube will form all over the chip. So what we did, like we coat a very tiny thin layer of iron or nickel or cobalt, that is catalyst, heat up little bit so that it forms island. Then there are heaters here, there is heater, there is heater here, which will locally heat and take this portion at 600 degree to 800 degrees centigrade, so that carbon nanotube only forms here. So these are maybe used for these particular places, maybe used for developing sensors. Okay, and there are circuits around it, but those circuits will be at room temperature. Only we are heating locally, and this way you can make you can develop carbon nanotube on the CMOS platform itself. Okay, but you have to do it in your own lab. You can't do it on the CMOS foundry. Okay, and so on. So there are ways to and people have developed ways to integrate nanomaterials or nanostructures which is beyond which is not silicon based. Okay, and you can add such nanomaterials or integrate nanomaterials at different different point of your CMOS fabrication. So let me just let me skip all this. Yeah, so these can be pre-CMOS, this can be intermediate CMOS, this can be post-CMOS. What is pre-CMOS? So before making the CMOS process, if you integrate your nanomaterial based sensor or MEMS based sensor and so on and so forth, then you send the wafer to your foundry and they fabricate your circuit which is required for your sensor. Okay, so that's basically pre-CMOS. So before actually fabricating your circuit, you fabricate your sensor and other devices which are not supported by the CMOS foundry. Okay, and then you develop your circuit. What is intermediate CMOS? Intermediate CMOS means maybe different layers you are fabricating. You are fabricating different layers. You remember oxide, then polysilicon. You need to implant, realize the gate oxide, polysilicon. Then you implant, realize source and drain, either ion implantation or diffusion. Then you realize you fabricate different metal layers, different oxide layers, and so on. So these are different layers you need to fabricate, right, for the CMOS process to make your circuit. So what you do is like you stop in intermediate somewhere at appropriate time, you make your sensor, and then you finish your other fabrication of other layers. So intermediate, that is intermediate CMOS. So you stop at some intermediate step, and you make your sensors, nanomaterial based sensors and other devices, non-silicon devices, non-CMOS devices, and you bring back and finish your CMOS process. Okay, and there is post CMOS. Post CMOS is your nanomaterial based sensor you integrate later on. Later on means after having the whole CMOS process, they will give you the wafer, and you then in that wafer or in that chip you can then make your own sensor. So that's like post CMOS. So all these processes has their own advantages and disadvantages. For example, if it is a pre-CMOS process, the advantage is you don't have to bother about temperature. There is no temperature budget. Okay, but the thing is you really can't use pre-CMOS process, because in case of pre-CMOS process, what happens is these CMOS foundry, they are very paranoid about their purity and all that. So if you put any foreign material in the CMOS wafer, okay, in your silicon or gallium arsenide wafer, they will usually not allow you to give that wafer for their processes, fabrication processes, because they will say that your the wafer already contains different material which is non-silicon, so I am not allowing you. Okay, so this pre-CMOS integration is mostly true if you have your own foundry. Say if Intel has their own foundry, if Analog Devices has their own foundry, they can make their own sensors beforehand and then use their foundry to develop the integrated circuit required for their sensors. So the pre-CMOS, although it sounds very good because you don't have the in temperature budget for developing your sensor and other devices, but this is accessible only those who have their own fabrication lab. Okay, you can't, I can't have develop my sensors and other devices in my lab and then send the wafer to TSMC to say that okay, now fabricate my circuit for my sensors. So they will not allow us to do that. Okay, but pre-CMOS has that advantage of temperature budget. What about intermediate CMOS? Intermediate CMOS, as I said, like it is like in between. You stop the process, you bring out the wafer, you develop your own device, you then bring back send back the wafer and they will fabricate it for you. Again, it has some advantage in the form of the temperature budget, and you can appropriately fabricate your device whenever you need it, and so on and so forth. Again, this is not supported by usually by industry, because the fabrication labs, because they said like your wafer is now contaminated. Okay, contamination is a big issue, is a big issue in fabrication. So what you can end up with, you will, most of the labs, they can use like post CMOS integration, where this carbon nanotube fabrication was a post CMOS integration, as I showed you. So we have already the your IC, your fabricated IC, your fabricated circuits, then you develop your sensor and other devices in a specific place. Okay, but if you do that, you have to make sure there is a thermal budget. You can't use any temperature you want, you can't use very harsh chemicals, because that can be detrimental for your circuit. Okay, and so on. So but you can use materials, non-CMOS, non-silicon materials, because CMOS foundry can't tell anything to you, because you are not sending back the wafer, so you can use any material which is appropriate for your device. Okay, but you have to maintain the you have to do processes below 450 or 400 degrees centigrade. You have to do the processes using green synthesis technique, that is the technique where you don't use harsh chemicals and so on. Okay, what else? I'm just keeping all these just to show that we have developed like sensors on filter papers, and there are research have been going on to develop various nano devices, for example, to mimic human organs. For example, electronic nose is one of the organ where basically you mimic your nose using various sensors, because our nose have several thousands of receptors to smell things. Okay, but there are sometimes it is difficult if you have like toxic gases and all those things, and sometimes some gases they don't have smell. Okay, so it is very difficult to detect through your nose. It is not advisable also. So people are developing electronic nose using the nano sensors and so on and so forth. Just skipping all this, don't need just don't need for this. Now last point I would like to mention before I stop this discussion is like there are a couple of approaches. One approach, as I said, like for integration. Okay, one is like, as I said, pre-CMOS, one is intermediate CMOS, and one is post CMOS to integrate integrate your circuit with your non-silicon devices. Okay. Now the thing is that is true for monolithic approach. By monolithic I mean you have a chip, you have a silicon chip, and there are circuits here, okay, on that chip, and maybe developing your device which is non-silicon device, maybe sensors as I said, on the same chip. So that's basically monolithic. On the same chip you are developing your sensors and your circuit. Okay, that has lot of advantages, some disadvantages also. But if you want to do that, you have to follow this, either pre-CMOS, intermediate CMOS, or post-CMOS integration, because your circuit and your sensor or other device on the same chip, right? So here you see sensor array and interface electronics are both incorporated on the same chip. Significant reduction in noise and crosstalks levels. Why there are noise and crosstalks? Because there will be lots of, if you do it separately, there will be lots of, so another approach is hybrid approach. One is monolithic, one is hybrid. What is hybrid approach? In the same package. So you ultimately you need to put it in a package. Okay, if you open up any electronic gadgets, you will see packages like this with legs, and those is basically covered, and all this you need to connect with a bond wire with the legs, right? So that you can access from outside. Here in hybrid approach you have two or more separate chips, so it's like system in package kind of thing. So there is a sensor which is in a separate die, there is circuit in a separate die, there might be multiple sensors on separate multiple dies, okay, and so on. So you need to, between sensor and circuit also you need bond wires. Okay, so there may be separate sensors to connect with the circuit, because they are sitting on different separate dies. Here they are on a single die. Okay, so in the hybrid approach, the sensors and circuit on separate die, but they might be on the same package. But if you are in separate die, there will be lots of bond wires. So these wires are often unpredictable in a sense ki how much capacitance, I mean there are models, but how much capacitance and inductance parasitic they might give. Okay, so these but if you do it on the same chip, of course there is metal tracks, but those metal tracks are more predictable, less parasitic capacitance and inductance. Okay, so that is why it is written that significant reduction in noise and crosstalk levels when you go for monolithic approach rather than hybrid approach. Okay, and good matching and reproducibility, because these metal tracks are very reproducible. Okay, but here these bond wires are not reproducible, some length may be different from the others, and so on and so forth, right? But the thing is here, it is not easy to develop things in monolithic approach. As I said, like there are pre-CMOS, there are intermediate CMOS, post-CMOS. That is how is the way forward. Maybe the post-CMOS is the only way for the masses, right? For us now, and also like a defect in sensor or these non-conventional silicon devices, okay, may result in failure of the complete microsystem, and you need to throw it away, right? But here, if it is a hybrid approach, okay, there are several advantages. One of the advantages is you can make these devices from other foundries also, non-silicon foundry. Okay, you can make these devices, and then you can integrate. You can connect them with bond wire and connect them with your circuit. So here there is no temperature budget, there is no of making those devices, there is no constraint on which material to use. We need to use green synthesis technique, or we can't use harsh chemicals, and so on and so forth. This is not valid here. Okay, so that is major advantage. But the disadvantage, as I said, parasitics due to interconnect is quite large. And that is unpredictable, less repeatable. Okay, and you have to do these things manually, usually manually. Of course there are automation in bonding as well, but the thing is, if you do things here, it's usually not manual. Okay, and so on. So there are hybrid approaches to integrate with CMOS, and there are monolithic approaches. So I think with this we should close this discussion on IC roadmap. And if you have any doubt, please raise your hand. Otherwise we will discuss little bit on Rajavi's book on the scaling short channel effects before we close it completely. So if you have any doubt, please raise your hand. Whatever we have discussed so far, because a lot of the thing I have gone through very quickly, and maybe because maybe you haven't heard about those, and then it will be difficult probably to follow. If it is so, I can repeat. Please let me know. So no comments. Everything was okay. Was I very fast?
No,
Sorry.
it was clear, sir.
Okay? It was okay. Right. So no part I need to repeat. Okay. Then it's fine. Um, so we uh, okay. So we did talk about scaling um, briefly. So this was the slide where we talked about scaling. Okay, you remember, and we did mention that um, we will calculate some of the things um, here, which I have written in this table through Rajavi's book. Okay, just to show that, for example, mostly like constant using constant field approach, we will calculate some of the things. For example, current, that current is decreasing by alpha times. Talk about capacitance associated with gate capacitance, that is decreases by alpha times, and so on and so forth. So let me calculate those things little bit, and then talk about briefly about the effect of scaling. Okay, because although we mentioned high K dielectric and strain silicon, but there are other things which I should mention right now. So So you know that if we try to calculate some of the parameters associated with FET while we scale down our FET device, okay, and we said that we need to scale down dimensions of the FET, okay, different dimensions. So so this is the uh, we know that this is the current at the saturation region, of the FET. So if we scale it down, okay, that's the drain source current. If we scale it down, you see this Cox will have this, because what is Cox, will, you know, Cox will have like the effect of Cox is epsilon by D. Okay, Cox is capacitance, gate capacitance per unit area. Okay, so gate capacitance is basically epsilon by D or epsilon by Tox, and Tox is, so if I, this gate capacitance is nothing but epsilon by Tox, right? And due to scaling, this will go to what? Epsilon Tox by alpha. So effectively it will becomes alpha Cox, right? So that is what I have written here, right? So this is, if I look at Cox scaled, so that will be alpha Cox. So I have written here alpha Cox, okay, and that is W by alpha over L by alpha. You remember, here I am saying that alpha is more than 1 and we are scaling down different dimensions, right? And of course, if it is like constant field scaling, we need to scale down the voltages in the same proportion, right? So if we do that, if you remove all this alpha and if you reduce, simplify the expression, you will ultimately get in other words, uh, this is reduced by alpha times, okay, due to scaling. That is what we have mentioned, um, that is what we have mentioned here. You see current is reduced by alpha times, okay, in constant field scaling current is reduced by alpha times. So that is what I am showing it here to you, okay. There are other parameters you can look at. For example, those capacitance associated with your channel, okay. I mean, same result is true here also. I mean, capacitance, the total capacitance, channel capacitance, okay, that will be, sorry, I mean, we can just skip that, skip that. So you see this overall channel capacitance is also reduced by alpha, okay. You can also do similar things for as far as the depletion width is concerned, okay, to calculate source and drain junction capacitance. So you have source and drain junction capacitance, right, associated with, so there is depletion layer. So these depletion layer will basically, so this will create capacitance, right? So these source and drain capacitance also you can calculate using formulas for where first you have to find out the depletion width, Okay, and if you remember, depletion width of a PN junction is uh, is given by like this, where Na and Nd denote the doping levels of the two sides of the junction, and phi b, I think these are known, but just let me, um, that's basically Kt over Q, ln Na by Ni square. Okay, and Vr is the reverse bias voltage. Okay, because this is in reverse bias, right? Reverse bias voltage, and the built-in potential phi b is a weak function of uh, basically with NANT, and in fact it increases if NANT is scaled up by alpha square, right? For now we are just assuming that Vr is much better than phi b. Okay, and just neglecting this second this part. So we can have like WD, that is the WD is depletion width. Okay, this we can write uh, 2 epsilon, that is the dielectric constant associated with silicon. Okay, so that's basically 2 epsilon for silicon, 1 by alpha Na. Okay, so the doping concentration needs to increase in your scaling effect. You need to increase your doping concentration. So it will go alpha times, both these will go alpha times, whereas this Vr will reduced by alpha times. So if you check that, you will see that this is 1 over alpha WD. Okay, so you see your depletion which will also reduced, reduced by the same amount, and so on and so forth. So I'm just leaving it. There are other calculations also possible with the same direction. Okay, and it is possible to show that your CS, source and drain scaled. Okay, source and drain scaled will be reduced if you reduce the scaling, if you go on having the scaling effect. Okay, um, now the thing is, in case of digital applications, as you see that scaling in will improve the gate delay. Okay, and power dissipation. How it will do that? Because in case of CMOS, the delay is basically C over I. Okay, sorry, right? So this is the delay associated with CMOS. Okay, now you can, if you look for scaling effect. Okay, you you will have all these whatever capacitance we have discussed so far. You see all these due to scaling effect, all this will decrease. Even your source drain capacitance will decrease by same amount. So this will decrease, current will decrease, and your supply voltage will decrease. So you will end up with uh, so the delay will decrease by alpha amount. Okay, what about power consumption? Power consumption uh, in a digital circuit. So in a digital circuit, power consumption, you know, C VDD, frequency term, and then C VDD square. Okay, so you see the, in this case also, if we don't talk about frequency, if we keep if we don't uh, if we keep our frequency constant, okay, then you see p scaled will degrade or will improve drastically, right? Will improve drastically. P scaled will improve drastically, and so on. Okay. Um, if you think about your analog circuits, maybe if you interested to for GM, okay, you know GM is mu Cox W over L VGS minus VTH, okay, that's basically your GM, okay, and if you find GM scaled, GM will not change, sorry, alpha Cox W by alpha, L by alpha, and also VGS by alpha, VTH by alpha. Okay, so that GM will remain the same, and so on. So these are different parameters you can calculate and tally it with the table which I have provided in the PPT. Um, now, as you see that so you can see the C current, the power, the delay, the power dissipation, and so on. Okay, so these you can see and tally it with your calculations. So one point I did mention in the while I was discussing things is this voltage scaling and constant voltage scaling and constant field scaling. And let me reiterate once more, this constant field scaling has several advantages, as you see, particularly for delay and power and all that constant. But one of the disadvantages, we need to reduce the voltages, because in all these cases you see we are reducing voltages and supply voltages, but it is not easy to reduce supply voltage drastically in the same proportion. Particularly this is not beneficial for analog circuit designer. So people, as I said, people tried constant voltage approach also, but constant voltage approach is detrimental in a sense कि your electric field will increase because you are not reducing the supply voltage, and that will be detrimental for your device reliability and your power consumption point of view. So people look for the generalized approach. Now the thing is, if you look for, if we go on reducing the device dimension, there have been different challenges pop up in last 30-40 years, and these are known as short channel effects. So, so there are different short channel effects out there, okay, um, and people use different means to improve those short channel effects. Okay, one of the short channel effect is threshold voltage variation. So these you can find in Rajavi's book, all the calculations which I made here, and whatever I am discussing now, you will be able to find it in the Rajavi's book. Now this threshold voltage variation, why it comes when we reduce the dimension of the MOSFET. Now the thing is, uh, if you look at long channel and short channel carefully, okay, this is my channel here, and there is the depletion region here, you see. So depletion region is under the channel and also here as well, under the source and drain. Now in case of long channel, when we talk about threshold voltage, okay, so there is a polysilicon gate or metal gate, whatever it is. Now this supply voltage, we need to form this channel, okay. So the threshold voltage, whatever is this immobile charge has an important role to play for the threshold voltage, right? Now you see, when we look for short channel devices, source and drain are very close. Here also the same fashion, the depletion region. Now if you look carefully, I mean, the depletion region is within source and within drain also, right? So these are immobile amps, right? Now you see immobile amps here, they are being imaged by so immobile amps here and here, they are being imaged by this, by the immobile amps in source and drain. This is true here also, okay, this is true here also, but that in the long channel, if in the long channel FET, those 2, 3, 4 immobile amps, I mean few immobile amps imaging doesn't matter. But here you see, if some of the immobile is, because they are so close and the number of immobile amps under the channel is very less compared to that present in the long channel MOSFET. Now if some of these immobile amps are being imaged by the immobile amp present in the source and drain itself, then from the gate side what you will see, you have to create less, so from the gate side you will see you have to create less number of charges here to mirror this, right? You have to, because this is a capacitor effectively, right? So you see the gate will now see that you need to image less number of charges, so that will reduce the effective threshold voltage, okay, or threshold voltage is going to vary. So if I plot VTH versus channel length or effective L effective, okay, you will see that with reduction in channel length initially, the voltage will not decrease, but if we keep on reduce it, at some point with channel length there will be reduction in the threshold voltage, okay. So that is one issue because simply because some of the immobile amps will be imaged by the source and drain depletion region, not by the gate itself, right? So that's one part. Second part is uh, or second short channel effect is Dibl, DIBL, that is known as drain induced barrier lowering. Again, I'm pretty sure you have heard this before. Okay. What is Dibl or drain induced barrier lowering? If you understand MOSFET, okay, I'm pretty sure you do. Then you see if I draw the barrier faced by the carrier when they try to move between source and drain. Okay, so the barrier is like this. So let me draw the energy band diagram. Say this is my Fermi level. So this is my n plus source and drain. Okay, and this is my gate. This is p-type substrate. Sorry. So this n plus and n plus having Fermi level close to. So this is my conduction band. Okay, and this is my valence band. So you see here the source and drain Fermi level is close to very close to the your conduction band, and in the substrate the Fermi level is little bit close to valence band. Okay, because it is a p-type, lowly doped p-type, right? Now the thing is, so the electrons here will not be able to cross the barrier and go to drain. Now when you apply bias gate voltage here, these barrier will be lowered. Okay, these barrier will be lowered, and then the electrons will be able to flow from channel, ultimately will be able to flow between source and drain. So this gate voltage will basically change this barrier height. Now instead of gate voltage, if you apply drain voltage here, here VDS, if you apply, say their gate voltage is no gate voltage is there. Okay, if you apply drain voltage, then what will happen? This will be lowered because we are applying drain voltage. If you apply more drain voltage, this will be more lowered, right? But still from the source side, electrons will not be able to cross the barrier. Now what will happen? This is I'm talking about short long channel. But now if it is a short channel MOSFET, okay, source and drain are very close. So let me draw it again, right? Source and drain are very close. There is no current between these electrons. These electron can't cross the barrier. Now I have applied. I'm only talking about there is no gate voltage. Okay, I'm applying voltage between drain and source. So what will happen? Again, the barrier from the drain side will start decreasing. So if we keep on increasing VDS, we will ultimately see the barrier at the source side will start decreasing, and then electrons will be able to flow. So this is known as drain induced barrier lowering. So drain side, by applying voltage at the drain side, you will be able to lower the barrier near source. And even if your VGS is 0, or maybe VGS is less than threshold voltage, and you haven't doing anything from the gate side to reduce the barrier, okay, what you can do when you apply bias, okay, you see, but by applying drain voltage only, you will be able to switch on the device. That means by reducing the barrier height near source. So that is known as drain induced barrier lowering. This will be detrimental for the short channel device, short channel MOSFET. So this is one of the short channel effect known as DIBL, or drain induced barrier lowering. So I am stopping it here today. If you have any queries, we will please raise your hand and then we can discuss. Did you understand this, whatever I have discussed now? If you have any doubt, please raise your hand. Okay, no doubt. Right. Okay, so we will stop here today. Start things tomorrow. So we will. So from next class onward, we will definitely meet at 8, and we will definitely meet at 12. Okay, there should not be any delay. And I will make sure that I will start the class sharp at 8. Okay. So thank you very much for your attention.
Thank you, sir.
Yeah.
Yes.
Thank you.
Thank you, sir.
Yeah.
Sir, could you upload